Hello, this is Mr. Leapforth, and we're going to try to put together a 15-minute, hopefully, review of the different topics and things that you would need to know for the geometry second semester exam. There was 6 units this semester. I would, review chapters 1 through 7 from first semester, but the focus of the exam will be on these chapters. We have chapter 8, which was on similarity. Okay, so you would want to review that. Chapter 9 was on different types of right triangles and the rules that go along with that. We did a unit 9.5. It's not a chapter in the book, but we took arc length and trig and made it into its own little unit. Then we talked about circles for a while. We did area in chapter 11, and surface area and volume is what we finished off with. And throughout all this, we did some stuff from chapter 13, which was on graphing. All right, and remember, you can stop the video at any time. You can scroll forward, scroll backwards, so you can pause it and write some of this stuff down. So the first section, 8.1, I'm just going to go through chapter by chapter. We'll start with chapter 8. The first section, 8.1, was just about ratio and proportion. One of the main ideas from this chapter is the idea of proportions, that you can say like x over 2 equals 5 over 10. Maybe I'll make it 100 just for fun. So, once you set up the proportion, we talked about the means extremes product theorem, or cross multiplication. And so you can solve problems out, which sometimes work out nicely, sometimes work out to be nasty fractions. Let's say we got 2 is to 5, like 8 is to x. You can cross multiply there and make it 2x equals 40, and so x equals 20. So throughout the entire chapter, you'll have to do stuff like this. So cross multiplication is important, and I paused the recording and I put some information about similar figures. We talked a lot about similar figures in this chapter, and there's 2 facts that are true about similar figures. Corresponding angles are congruent, and corresponding sides are in the same ratio or proportional, and we'll use that to set up a bunch of cross multiplication or means extremes product theorem problems. The next section highlights how to prove triangles similar. There was 3 different ways that we talked about. Whoops, I was supposed to highlight that. Sorry about that. Angle similarity, side similarity, and side angle side similarity. The angles should be congruent and the sides should be proportional, and so you'll want to prove that, although there won't be a lot of proofs on the semester exam for this semester. It's mainly algebraic and formula based. After that, after you prove the triangle similar, you can say the corresponding angles are congruent and the corresponding sides are proportional. So that was like our CPC-TC for congruent triangles. For similar triangles, once you prove them similar, then you know all the similar figure ideas that we talked about up here are true. And then you get to section 8.5. 8.5 had three theorems that we want to talk about. The first one is what we call the side splitter theorem. The side splitter theorem, should have written that out on a pause, but you can write it out with me. I spelled theorem wrong. This is embarrassing. You guys still watching? Don't look at that part. Alright, so side splitter theorem, and I kind of don't like how that's right in the middle. As long as you have the parallel set up as I do in this picture, I can probably just stick some numbers in like 2 and let's do 10 and 3 and x. As long as you have these sides here and here parallel, the sides are split proportionally. So you can set up a proportion 2 compares to 10, like 3 compares to x. I like to just do top to bottom, and then we would solve it out. And I'm guessing you guys know how to do the cross multiplication there. So let's go back and say, what if this side down here was 5? And this was y. How do you figure that out? Well, in the same picture, you have this triangle similar to a bigger triangle, and so we want to look at the sides there. So you can also set 2 from the little triangle as it compares to 5 from the little triangle, and then you can look at the big triangle and say 2 plus 10, so that's 12, compares to y, and you can do your cross multiplication there as well. Is that good? That's what we wanted, right?
Or you can do 2 to 10 and 5 to 1.
That's the common
2 to
mistake,
12.
right? 2 to 12, right?
2
Yeah.
to 12.
2 to 12, 2 to 12, and 5 to y also works. Yeah. Cool. All right. The second theorem from there was similar to the side splitter. What you have is you have 3 parallel lines, 1, 2, 3, and there's a couple transversals coming through. And you can also have, 5x, 7, it doesn't really matter. And you can say 5 compares to x, like 7 compares to 21, and then you can do your cross multiplication from there. The third theorem from section 8.5, and you can spend some time reviewing this as well. It's called the angle bisector theorem. And as long as the angles are bisected, again, just making up some numbers here, 3 and 8, you can say 2 compares to x like 3 compares to 8. So those were 3 pretty important theorems which allowed you to set up proportions, which you solved in the way you solved a lot of other things from the chapter. Chapter 9 was all about right triangles, so there's some radical review in 9.1, a little bit about circles in 9.2, but really we want to start our work in 9.3, so you should draw a right triangle on your paper. And what we want to do is, this is the hypotenuse down here. We want to put an altitude. An altitude, remember, is perpendicular. We want to put an altitude on the hypotenuse. So this is our altitude on hypotenuse. From 9.3, these are the altitude on hypotenuse theorems. So I think it's probably best if we just do some examples of the altitude on hypotenuse theorems really fast. I'm going to call this A, I'm going to call this B, and I'm going to call this length C, and let's just use 9 and 4 as our lengths there. So the whole hypotenuse is, class, you guys awake? What's the whole hypotenuse? If we have 9 and 4, what's the sum? Crickets. Crickets. Anybody know what happens when you put 9 and 4 together? You guys still with me? You add them, and what do you get? What do you get? 13. All right, just making sure you guys are still awake back there. So you have 3 altitude on hypotenuse theorems. You got a squared. They were a little shy for the camera here. A squared. What you want to do is its shadow, we called it, or its projection. So a squared equals 9 times the entire hypotenuse. Alright, you can also use the other leg squared equals its projection times the entire hypotenuse. So again, what we're doing here is we're taking a leg squared, it's equal to what we called sometimes its projection times the hypotenuse, the entire length there. Okay, so that's 2 of the sides. The third side can be found by taking the altitude and squaring it, and that's like projection 1 times projection 2. And so in our example, it's b squared equals 9 times 4. And so you probably want to pause the recording and write that down at this point. In 9.4, we did probably geometry's most famous theorem. You got a leg, and a hypotenuse. The Pythagorean theorem says that leg squared plus leg squared equals hypotenuse squared. I don't think we have to spend too much time on that because you guys should be pretty familiar with that. And connected to that is the distance formula that says the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. That's a formula that you want to have down and be able to use to find the distance between 2 points. You can always use the Pythagorean theorem for that if you want. We got into a bunch of triples. The triples that I would want to have you remember are the 3, 4, 5, the 5, 12, 13, the 8, 15, 17, what else? The 7, 24, 25. Those are probably the main ones. Sometimes we stick the 9, 40, 41 in, and what? 11, 60, 61. Remember, the biggest side has to be the hypotenuse, and those might help you out. Remember, I can double any of these. I can make it like a 6, 8, 10, for example, times 2. So you can have other Pythagorean special situations as well. And then we got into the 30, 60, 90 rules. So it's probably best if I just do some examples for that as well. Let's say you have a right triangle with a 30-degree angle, a 60-degree angle, and a 90, of course. Let's say the side across from the 30 is 5. The side across from the 90 is twice as much and the side across from the 60 is that number across from the 30 times the square root of 3. So if you can remember those rules. You know, additionally, you got the 45, 45, 90, which is an isosceles right triangle. Whenever you have the isosceles right triangle, you know it's like 10 and 10, and the hypotenuse is going to be that times the square root of 2. There's more complicated problems that come up, but we can review those in class. 9, 8. Okay, go ahead, Mr. Coach.
Special triangles you should put in there.
This is special. These are the special triangles, and that was from section 9-7. And so you want to highlight that. 9-8 was three-dimensional. We didn't do that.
Trigonometric ratios.
9-9's trig. We're going to do that in Unit 9-5 in a second, and that's it for Chapter 9. All right, in Unit 9-5, we talked about arc length and trig. Sorry, the video's a little choppy. Probably all of a sudden this appeared out of nowhere, but you know, remember you can pause and use this however you want. The arc length, you know, we're back to circles. I think somewhere in here I can get a fancy circle out. So arc length, when we find arc length, what we want to be doing is just finding the piece of the circumference, and we want to know how long it is. So usually we have some central angle. We'll call it theta. All right, and to find the arc length, you know, the circumference formula is 2 pi r, so you should have that down. The arc length is just some fraction out of 360 of that circumference. And so theta, remember, is the central angle, and r is the radius. So if you have those two pieces of information, you can get the arc length out. As a result, we did some problems on that in 9-5, and then we jumped to this trig idea. So let me give myself a little bit more space. So you have a right triangle. Let's just make an angle theta again. We have a side opposite theta, we have the hypotenuse, and we have the adjacent. So those are our sides. We talked about the sine, cosine, and tangent. We talked about how the sine of theta is opposite over hypotenuse. The cosine of theta was the adjacent over the hypotenuse, and the tangent of theta is the opposite over adjacent. And some people said like so, ka, toa, had fancy ways of remembering that, but we were able to set up problems from that. You remember we used our calculator to do problems. We did some word problems with that, but you know, trig was a pretty central idea to this unit. A couple quick calculator problems. You know, if you want the sine of 60, you know, you hit the sine button, and then the 6 button, and then the 0, and then you hit equals. Some calculators you do 6, 0, and then sine. So if you want the sine of 60 degrees, basically you just type it in. But sometimes I'm given, you know, the ratio, and I want to know what angle I'm talking about. And so in those problems, you do the sine inverse of a half. It should spit out something like 30 degrees. You want to make sure you're in degree mode in your calculator, and you should practice that a little bit. I like the sine of 30. I know it. It's a half. The inverse sine of a half is 30, so that's a good one to practice to see if your calculator is working correctly. And good luck with the trig problems.